Today, inshallah, we are going to cover section 2.5 about what is called LU factorization of a matrix. We are going to write the matrix, the coefficient matrix A as a product of two matrices. One of them is lower triangular and the other is an upper triangular matrix. Okay? We'll see how to do this and how to use this factorization to solve a system of linear equations, and to see what are the advantages of using LU factorization in solving the system. And then we're going to count the number of operations for the different algorithms, such as Gauss elimination, Gauss-Jordan, and so on. So let's first review quickly the elementary matrices. Do you remember the elementary matrices? Okay, you will do one of the row operations on the identity matrix to obtain what is called an elementary matrix. So this guy is an elementary matrix. What is the operation? Interchange of the first two rows of the identity matrix. Do you remember its inverse? How to get it? The same. You can get it using Gauss-Jordan. Put I to the right and do row operation. You are just switching the first two rows, so you'll get the same matrix for the inverse. So this is the inverse of E1. And the effect of multiplying any matrix from left by this matrix, the result would be, again, the same operation on this matrix, which is the interchange of the first two rows. Okay? And this is another elementary matrix, which is corresponding to scaling the first row by half. For the identity matrix. And what is its inverse? Instead of half, you write 2. Okay, so multiply these guys, you'll get the identity matrix. So this is its inverse. And its effect again, if you left to multiply by another matrix, it will do the same effect, which is scaling of the first row by half. The third type, which is row replacement. Here we replace the second row of the identity matrix by the sum of the second row and double the first row. Yeah? The operation actually is R2 plus 2R1 is going to replace R2 in the identity matrix. Do you remember its inverse? ممكن بالبارتيشنينج. اوكي. طب هيطلع ايه؟ negative 2 instead of 2 مش كده؟ And if you do again left multiplication with another matrix, you will get the same effect on your matrix. The sum of the second row with double the first row. Okay. So to summarize, we have three types of the elementary matrices. And each row operation can be replaced by, or can be equivalent to, left to multiply your matrix by an elementary matrix to do the effect of the reduction. So let's look at the replacement operation for the elementary matrices. If you look at these two elementary matrices, are these elementary matrices? What are the row operation on I? The first one actually is this guy on I. What about the second? R3 minus 3 R1 R3. Are these matrices triangular matrices? Lower triangular matrices both, مش كده؟ And their inverses triangular matrices. I have to change the sign of the multiplier actually. So instead of 2, you write negative 2. Instead of negative 3, you write 3. So the inverses are also lower triangular matrices. مش كده؟ What about the product? E1, E2. Is it triangular matrix? Let's multiply E1, E2. First 1, 0, 0. And then 2, 1, 0. And then negative 3, 0, 1. Is this an elementary matrix? No, this is not an elementary matrix. Okay. However, it is triangular matrix, lower triangular. With diagonal, if you look at the diagonal for all matrices, the diagonal entries are all ones. Okay. So when you apply reduction and do the replacement operation, the elementary matrices used are lower triangulars with diagonal entries of all ones, and the product of these elementary matrices is also a lower triangular matrix with ones also on the diagonal. Okay? We want to use this fact to do the factorization of the matrix A into the product of two matrices. One of them is lower and the other is an upper. The objective of this factorization is to solve again the system X equal B. Suppose, for example, that I have this matrix A and I want to solve X equal B for different B's. I have different B's and I want to solve the system X equal B. However, I don't want to do the reduction every time you get new B, so I want to do the reduction once. So let's do the reduction once by obtaining what is called the LU factorization of the matrix A. So suppose, for example, that I could factorize the matrix A into the product of these matrices. If you look at the two matrices, the first one is a lower triangular matrix, and the second one is an upper triangular matrix. I'll show you how to get these matrices. Suppose that I have these matrices and I'm solving AX equal to B. Now I have A as L, U. So I get this equation LUX equal to B. I know now L and U, and I'll give you B. Okay, so the unknown here is X. I want to solve this guy for X. So I'll solve this in two steps. The first step, I can call this guy as a new vector, Y. However, Y is still unknown because you don't know X, right? If you look at this system, Ly equal to B. You know L and you know B and you don't know Y. If you write L, your lower triangular matrix, so write something like this. and here your y vector equal to b. Do we need to do any reduction to solve this system? No, there is something better than partitioning. You can read the solution using what is called forward substitution this time. So y1 equal to b1 direct. And here you have an equation for y1 and y2, and you know y1 from the first equation, y1 equal b1. The second equation, minus y1 plus y2 equal b2, so get y2, right? And then go to the third equation, equation y1, 2, 3, you get y3 and so on. So this system, in this system you don't need any reduction. You can read the solution directly using forward substitution. Once you get the value for the vector y, you can then get back to this equation and write ux equal to y, where u is this matrix, which is actually in echelon form again. So you don't need to do any reduction and solve using back substitution this time. As you know u, and you get y from this step. So instead of doing any reduction, you can just read the solution using forward and backward substitution. So my problem now is how to write the matrix A as a product of two matrices L and U. So this is what I did on the board. You solve this guy for y. Once you get y, you solve ux equal to y using back substitution. So every time you get new b, you just put your b here, get y, and here to get x. The effort for backward substitution and forward substitution is less than the effort of the reduction. So this is the reason for doing so. Okay, and you apply it only when you have several b's or many b's. Okay, and you want to solve for each b, and b is changing, for example, with time. So every time you get a new b, and you want to solve the system. Okay, so you factorize a as L and U, and when you get b, solve two system without any reduction. Okay, is it clear the idea of LU factorization? Let's see how to get the LU factorization, how to get these matrices. Okay. Actually, we did the step of reduction as before. When you have A, you can reduce A to echelon form. This is actually how to reach U. So take your matrix A and apply the reduction until you reach the echelon form. The echelon form actually would be this guy, which is U. The problem now is how to write your L. Okay? So suppose that I did some row operation on A until I reached this matrix U. I did some operation on A, take 3 as pivot and eliminate negative 3, 6, and negative 9 to reach this column, and then take the second pivot and do elimination and so on. So I did some operation until I reached this guy. And from the theory, I know that these operations can be replaced by multiplying by elementary, left to multiply by elementary matrices. So I write this in elementary matrices form. So I can say that I did some row operations, and each row operation is equivalent to multiplying A by some elementary matrix until I reach the matrix U. For simplicity, assume that I did only one operation, which is the row replacement, like these guys. So these operations are E1, E2, and so on, elementary matrices multiplied from left to the matrix A until you reach the matrix U. You know from the previous example that these elementary matrices corresponding to these operations are lower triangular matrices, and the diagonal entries are all ones. So this is applied to all your E's. All these guys are lower triangular matrices with ones on diagonal. Right? So the product of these matrices is also a lower triangular matrix with ones on the diagonal. Okay? So let's get A from this equation. What is A? Multiply by the inverse of this guy. And this is actually can be written as inverse of E1 up to inverse of EP multiplied by U. The inverse of each of the elementary matrices here is also a lower triangular matrix with ones on the diagonal. So the product of these guys is lower triangular matrix with one on the diagonal. Actually, this is L. Okay? So this guy or this guy is L. So we can write L equal to UP E1, the inverse of these guys. Sorry, EP. So this is one way to get L. Okay? There is a simpler way to get L. If you multiply by the inverse of this guy again, you will get EP up to E1 multiplied by L equal to I. Right? Look at this equation and this equation. What can you say about these two equations? You did here some operations on the matrix A, you reached your upper triangular matrix. You did here the same operation on the matrix L to get the identity matrix. So actually to write L, you can simply do a simple trick to write L directly without evaluating this guy. Let's see it on an example to see how to write the matrix L directly using this property. The same operation on A to reach U are the same as the operations on L to get I. Okay, so let's see an example. Again, I am doing only row replacement operation. Row replacement only. I'm not going to do scaling or interchange. So if this is your matrix A, let's do the regular steps for reduction to reach the echelon form. So we'll take 3 as pivot, eliminate -3, 6, and -9. This is the first iteration. Then don't do any interchange, don't do scaling, take -2 as your pivot. Okay? Don't do any interchange, don't do any scaling, take this guy as your pivot, -2. And then eliminate or remove 10 and -16. Okay? So this is the second iteration. Next step, I'll take -1 as the new pivot and eliminate -3 until you reach U. This is my U. Okay? So this is the upper triangular matrix. I want to write the matrix L without evaluating this guy. Let's make use of this property.
تاني ستيب ده سوري اول ستيب احنا قلنا غيرنا اول رو اول كولم سوري
غيرنا ساين ايه؟
يعني مش احنا بقى اللي هي تاني كولم
هنا؟
هو احنا مش عملنا ده ماينس هنا ولا
عملت elimination النيجاتيف 3 و6 والنيجاتيف 9. ازاي؟ عملت addition للفيرست تو روز طلع الرو ده. multiply الفيرست رو by نيجاتيف 2 واد مع الثيرد رو هيطلع ده. elimination عادية قبل ما اعملها. طيب دلوقتي I want to do the same steps that I did on A. I want to do it on some matrix L to get the identity matrix. So I'm going to write the matrix L and I'm doing some elementary row operation the same as this guy to reach the identity matrix. I know that the matrix here is lower triangle, right? With ones on the diagonal. So I can write this directly. So I want to find these guys, right? Let's see what happened in the first iteration. In the first iteration, to get this 0, I simply added the first two rows. So I want to write something here to add the first two rows to get the first column on I, which is 1, 0, 0, 0. So what to write here? The same operation as you did here. You just added. So I have to write here negative 1 to add these guys to get this 0. For this guy to be 0, I multiply the first row by negative 2 and add it to the third row. I want to do the same operation here to get this 0. Multiply the first row by negative 2 and add. Multiply this guy by negative 2 and add with something here to get 0. I have to put here 2. For the third row, multiply the first by 3 and add with the fourth. Multiply this guy by 3, so I have to put here negative 3. Actually, what are these guys? اليوم تايتل عندنا النمبرز دي. multipliers. Are these the multipliers?
الفاكتورز اللي انا ضربت فيه
ما الفاكتورز دي اللي كنا بنسميها مالتبلاير. مش دي المالتبلاير؟ ده المالتبلاير بتاعنا. بس هو ده المالتبلاير فعلا؟
النيجاتيف بتاعه
نيجاتيف المالتبلاير صح؟ يعني هنا المالتبلاير بتاعي كان ايه؟ كنت بديفايد النمبرز، يعني مثلا بتاع اخر واحد كنت بديفايد نيجاتيف 9 اوفر 3 واتشينج الساين فيطلع لي المالتبلاير بتاعي ده كده المالتبلاير. لو يطلع 3 فكنت بقولها مالتبلاي الفيرست رو باي 3 واد مع الفورث رو. فده المالتبلاير بتاعي، انما اللي كتبته هنا ايه؟ نيجاتيف 3. فاكشولي النمبرز دي ده نيجاتيف المالتبلاير. في حاجة أسهل كمان من إن أنا أقول نيجاتيف مالتبلاير عشان ما يوجعش دماغي يعني. If you divide negative 9 over 3 you will get this number directly. صح؟ هو ده actually negative المالتبلاير. Divide without changing the sign. فبديفايد النمبرز by البيفوت. هو ده كان actually multiplier وبحط negative sign. So don't put the negative sign. So what happened in the second iteration? So this is for the first column here. What about this guy?
نفس الكلام بس 10 على نيجاتيف
نعملها بقى على طول. يبقى divide النمبر ده على البيفوت يطلع نيجاتيف 5. يبقى هنا نيجاتيف 5. وبعدين نيجاتيف 16 over نيجاتيف 2 يبقى 8. In this step, this guy was the pivot to reach this matrix. The next step, يبقى النيجاتيف 1 هو البيفوت مش كده؟ ديفايد بقى نيجاتيف 3 عن نيجاتيف 1 يبقى دي 3 بتاعتي. So actually we wrote L without any computation, just getting the negative the multipliers. انا بجيب المالتيبلاير ازاي عشان eliminate ال 6 دي؟ بقولها multiply الفيرست رو 6 over 3 with negative sign. ده المالتيبلاير بتاع ال 6 اللي هو النمبر اللي في الثيرد رو. صح؟ بجيبها ازاي؟ بديفايد 6 over 3 وتشينج الساين يبقى المالتيبلاير بتاعي نيجاتيف 2 فبقولها مالتيبلاي الفيرست رو باي نيجاتيف 2 واد كده ال 6 تبقى eliminated. اللي بكتبه بقى عندي هنا مش النيجاتيف 2 ال 2 اللي هي نيجاتيف المالتيبلاير. طيب يبقى زي ما اتفقنا this is u and L. بص كده احنا ممكن نعملها بجرافيكالي كده على طول ان انت هتاخد الفيرست column divide its pivot which is 3 and then take the second column بس مش كل الكولوم starting from the pivot. Okay, نسميه sub column starting from the pivot and divide by the pivot. You will get the second column or sub column of L and the third take from the pivot divide by the pivot and the last number is 1 and then put the 0 so this is your L. What about the determinant of A? 1? We have determinant of A equal determinant of L times determinant of U. But L actually is triangular with ones on the diagonal, so its determinant is 1. So determinant A equal to determinant of U. What is determinant of U? Negative 6. So this is the determinant of A from the LU factorization. It equals the determinant of U directly. So this is a special case when you do only the row replacement operation. There is a generalization for this method when you sometimes you have to do interchange to get your pivots. Okay, so for example, sometimes you have to do something like this. If the matrix is 3 by 3, so this matrix would interchange the first two rows. So in some examples, we have to do something like this, multiplying the matrix A by some, we say, permutation matrix to do the interchange, and this guy is going to be factorized into L and U. So this is what MATLAB do. So in MATLAB, actually, it uses this formula, PA equal LU, and this guy to do the necessary interchange to find all your pivots. But for the exam, I'm going to ask you only on this guy. Do only row replacement. You don't need to do any interchange. You will find all your pivots. In comparing different algorithms and solving system of equations, for example, I can solve the system of equation using Gauss elimination, Gauss-Jordan, using the inverse. I want to find which method is faster than the other. Okay? So to compare, you can do it experimentally, run the code for different problems and compare. But the most efficient way is to count the number of operations you do in each algorithm. So this is what is called the floating point arithmetic operations, or simply flops. So we're going to count the flops for each algorithm. So let's start with Gauss elimination with back substitution and see how many arithmetic operations do you need to get your solution. I'm going to solve AX equal to B. So we start by writing the augmented matrix. assume that the coefficient matrix is a square matrix augmented with B and do the elimination. Let's start counting. I'm going to count. So the first step is to find the multiplier. What is the multiplier? To eliminate this guy, for example, negative A21 over A11. So we have one division operation. We have one division. So what do we do next? We multiply the first row by this multiplier, add it to the second row. Okay? I'll get here 0, so you don't need to multiply the first guy and add it. So I start by from the second one. So multiply these guys by this multiplier. So how many multiplications? N. I need n multiplication. And then add two elements of the second row. How many additions? N addition. Sum these guys. So we have, let's sum these guys together, multiplication and division, and addition and subtraction together. So you have n plus 1, okay, multiplication and division, and n addition to eliminate this guy. في البي هنا معايا ما تنساش صح؟ I eliminated the first guy because I adjusted the first guy to get here 0. So you don't have to calculate this guy. So I started from this guy, you have n items. طيب ده كده عشان ايه؟ To eliminate this guy. So I repeat this for all these rows. How many rows? n minus 1 rows, مش كده؟ So I'll have n minus 1 rows. So let's write it here. So the first iteration, to get zeros here, I need n minus 1 rows multiplied by n plus 1 multiplication and division. N minus 1 rows multiplied by n plus 1 multiplication and division, and n addition. Right? معانا يا شباب؟ نريبيت بقى بعد ما تجيب هنا الزيروز هجيب هنا ده البيفوت الجديد بتاعي. يبقى في النكست iteration هيبقى فيه برضه 1 المالتبلاير 1 division multiplier والنمبرز دي هيحصل لها ايه؟ minus 1 مش كده؟ يبقى هتلاقي برضه 1 division n minus 1 بقى multiplication n minus 1 addition. How many rows? يبقى n minus 2 rows. And so on. Okay? So this is for the second iteration. So let's sum up these guys to get the total number of flops. So if you are talking about multiplication and division, so you have here n plus 1 times n minus 1 rows. This is in the first iteration. In the second iteration, collect some these guys, so you have n multiplied by n minus 2. Until the last iteration. In the last iteration, you will find that the numbers would be 1 row. You are going to operate only on 1 row, and you will have 3 multiplication and 2 addition. So I start with 1 by 3. So this is the number of flops for the multiplication and division. Okay, so we usually write it in compact form. This summation of, we write the general term here in terms of another variable, k minus 1, k plus 1, starting from k equal to 2 up to n. Okay? This guy can be written as summation k square minus 1. So this is the number of flops for multiplication and division. Let's count the number of flops for addition and subtraction. The last element would be n minus 1 rows multiplied by n. N minus 1 by n. And for the second iteration, you have n minus 2 rows by n minus 1. Blah, 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 blah. And the first term would be 1 row multiplied by 2. 1 by 2. So again, this can be written as summation of the general here, k minus 1 times k, and k starting from 2 to get these guys up to n. And again, this can be written as summation k square minus k. So I want to find these sums to get the total number of flops. So from algebra, actually, we can use these summations. Summation of k and summation of k square. Okay, this is actually an arithmetic series, and this is its sum, and this is for the sum of squares. You will get this form. I'll leave it for you as an exercise to sum up these guys using this formula. It's very simple. Okay, but make sure that you here start from 2, not from 1. If you collect these terms together, you will get something multiplied by n cube, by n square, and so on, and n and constant, and so on. So I'll take only the dominant term, the most significant, the highest power. So the highest power would be n cube. So, and this is its coefficient. So I can say that for large n, I can ignore n and n square and compare only just n cube term. So the Gauss elimination with back substitution, the number of flops is of order 2/3 n cube. Okay? If you do the same procedure to count the number of flops for the back substitution, this is for the reduction. Okay? If you count the number of flops for the back substitution, it would be this series, and its sum would be n square. So this is why we say that this guy is negligible with this guy for large n. If you have n, for example, 1000, so this is of order 10 to the power 6, and this is of order 10 to the power 4. Okay, so this is negligible with respect to this guy. So to summarize, for Gauss elimination with back substitution, we say that the number of flops is of order 2/3 n cube. If you do the same for other methods, do the same procedure as I did here for Gauss-Jordan, for example, to solve system of linear equation, ax equal b and a is n by n. And if you count the number of flops, it would be of order n cube. So this is why when you solve, we say that it is preferred to use Gauss elimination with back substitution rather than using Gauss-Jordan, because it is faster according to the number of flops. However, if you remember the partitioning, if you notice that your matrix, the coefficient matrix, can be written as block triangular, for example, we said that we can solve, instead of solving the big system n by n, we can divide the problem into 2 smaller problems, and each of which is n over 2 by n over 2 system. So if you did this and you want to find the reduction in the number of flops, if you solve a system n over 2 by n over 2, using Gauss elimination with back substitution, the smaller system. So you write the number of operation would be 2/3 n over 2 cube. But actually, we are going to solve two systems rather than one system. So multiply this guy by 2. So the number of flops when you solve a block triangular system would be 2/3 n cube multiplied by 1/4, which is simply you take 1/4 of the time if you solve the big system. So you are saving 75% of your time if you use the property that your matrix is block triangle. Okay? So you have to know this before solving or giving this to the computer to solve. You can save time if you know the structure of your matrix. To make sense for these numbers, for n equal 24, for example, these are the number of flops for the three methods. For Gauss elimination, you will have to do 9k flops. For Gauss-Jordan, about 14k flops. If it is block triangular, you will take 2.3k flops. The matrix inverse. If you do the same steps to find the matrix inverse, do you remember we can get the matrix inverse using Gauss-Jordan, the edge-get method. In Gauss-Jordan, you'll take 2n cube flops. And for the edge-get method, you take n factorial flops, which is very large number for large n. Do you know how many flops do you need for the LU factorization? هو Gauss elimination كان 2/3 n cube. ده Gauss elimination. What about LU factorization? تعال نبص على الافورت في LU factorization. ايه الافورت؟ I'll do reduction for the matrix A until I reach the matrix U, which takes 2/3 n cube. ال مش محتاج فيها effort of n cube. الافورت بتاعها هتلاقيه actually of order n square. فهيبقى negligible اصلا. فهتطلع برضه في نفس الاوردر of Gauss elimination. Okay. طيب do you know the fastest supercomputer in the world? Where it is now? The fastest supercomputer? Guess where? أمريكا. طيب هو في طبعا ايه competition رهيبة between China and USA. In 2016 it was in China the fastest one. However, in 2018 it was in USA the fastest one. This is the configuration. It has 4,6408 servers of 22 cores and a number of flops. Here, flops stands for floating point operation per second. Okay, so it can do 200 petaflops. كله على بعضه لا 4608 سيرفر كل واحد فيه 22 كورز وبيعمل لك 200 بيتا فلوبس اللي هي 200 مليون جيجا فلوبس floating point operation per second والرام بتاعته 10 مليون جيجا. طب even if you have this supercomputer and you want to find the inverse using the edge-get method.
fractions of seconds.
لا هياخد days برضه. عشان النمبر ده very large اللي هو 10 to the power 23 flops. فالedge-get method حتى مع السوبر كمبيوتر هتاخد days. انما عشان تجيب الجاوس elimination طبعا ايه؟ مفيش. الفاكتوريال ده رهيب. بص النمبر قد ايه؟ اوكي. طيب خلينا نشوف كده حاجة سريعة. We have another way to find the solution of system of equation. You can write A backslash B. On MATLAB, this stands for solution for the system AX equal B using Gauss elimination with back substitution. Or you can do something like inverse of A times B. So you can solve the system using Gauss or using the inverse. According to the theory, this operation takes about 2/3 n cubed. To find the inverse, how many operations do we need to find the inverse using Gauss-Jordan? Take about 2n cubed flops. So let's try this on an example here. I actually created a matrix A, random matrix. Its dimension is 4,000 by 4,000. I'm going to solve a system 4,000 by 4,000 and random vector B, and then get x using x equal A backslash B and x equal inverse of A times B. Okay. Tick and tock, these guys are used to estimate the time of the operation. When you put a function between tick and tock, it estimates the time for the operation. نعم. دي كده معناها انه هيsolve the system using Gauss elimination. طب اكتبها كده A backslash B. A دي coefficient matrix و B ده right hand side. خلينا نجرب كده نران. تتوقع ياخدها في قد ايه؟ 4000 في 4000. ده جاوس elimination. هيجيب الانفرس بقى ويسولف. theoretically المفروض ايه 3 تايمز تقريبا. قدها 3 تايمز. تقريبا صح؟ اوكي. خلاص كده خلص. على الكمبيوتر بتاعك المفروض يبقى فاستر. ده يعني لابتوب صغير كده سيليرون بروسيسور، يعني مش زي اللي شفناه من شويه يعني. فزي ما انت شايف كده سيستم 4000 باي 4000 ما بياخدش سكندز يعني عشان يسولف using Gauss elimination. اوكي. اي سؤال يا شباب في الليكتشر؟ يبقى النهارده عايزين نكون عرفنا how to find LU, when to use LU، وايه الادفانتج بتاعتها. يعني معانا اجابه على الاسئله دي. when to use it، يكون عندي several B's وعايز اصولف السيستم، والبي دي بتبقى changing، يعني انا مش معايا دلوقتي. حتى انا لو معايا دلوقتي كل البيز احطها ممكن واعمل الريدكشن، احطهم جنبي واعمل الريدكشن، بس هي البي مش معاك، كل شويه بتتغير. فكل ما تجيلي بي عايز اصولف، فالحل بقى ايه اللي معايا دلوقتي اللي فيكسد ده؟ ممكن يجي لك ايه بقى؟ في سيركت وفي سورس عمال يتغير على السيركت دي. اوكي. فالسيركت دي الاليمنتس فيها فيكسد، فالاي هي الكوفيشنت ماتريكس دي فيها الفاليوز مثلا بتاعت الريزيستورز اللي موجوده في السيركت، والفولتج ده السورس بتاعك ده بيتغير مع التايم، وانت عايز تشوف الكرنت هيبقى يتشينج ازاي اكوردنجلي. اوكي. فكل مره عايز اسولف سيستم حسب السورس الجديد اللي بيجي. ده مثلا اكزامبل، يعني ممكن يبقى سيستم ميكانيكال وات ايفر، يعني السيستم هو ايه، فورسز بتتغير عليه وانت بتشوف ايه شكل الرياكشنز عندك عامله ازاي. فلما يكون عندك several بيز وبيز مش معاك اوريدي عماله تتشينج وذ تايم، فده احسن حل. اخد الاي اعملها فاكتورايزيشن، تبقى ريدي معاك ال واليو. once you get B, solve two system using back or forward substitution. It will take 2n square flops. اوكي. عرفنا ازاي بنعملها ال يو مش كده؟ نعملها باوبريشن واحده، رو ريبليسمنت، اجيب اليو ومنها هقرا ال، وعرفنا نكاونت. اي الجوريثم كده تجرب في البيت كده، كاونت النمبر اوف اوبريشن according to السلايدز كده، المفروض تطلع الاوردرز بتاعت كل الجوريثم زي ما هو. أي سؤال يا شباب؟ شكرا جزيلا.